So hopefully people who are watching will in a moment see a slide. There it is. If anybody has any problems seeing the intro slide, do say something in the chat and we'll figure it out. But yeah, I encourage people to introduce themselves in the chat. I'm excited to be doing another webinar. I did a research webinar for Unlikely a few months ago, and I know that some people had some good conversations and made some good connections in the chat. And I feel like this is a topic of conversation which lots of people will have opinions on. So I do think it will be good to get a conversation going, but we'll have some Q&A at the end as well. But yeah, let's do some introductions then. So I'm Callum Hackett. I'm the head of research at UnlikelyAI. I've been here for about 2.5 years. Previously, I've done various bits and bobs in AI, but the most relevant thing to this conversation is that I've worked in a bit of cognitive linguistics, stuff to do with the evolution of human intelligence. And my colleague, Louis, is a senior applied scientist here as well. So Louis, do you want to introduce yourself?
Yeah. Hello, everyone. I've been here as senior applied scientist since September. And Unlikely, my background is AI research, mostly in an academic context. So I was research at Edinburgh University for a few years before I came here, and that was in various parts of machine learning and AI, some neurosymbolic, some unsupervised learning, some just regular deep learning stuff. Yeah.
Cool. So this webinar is going to be broken up into 3 segments. In the first segment, I'm going to give you a presentation which will talk about a broad topic of the relationship between human psychology and AI. After I've given you some of the context on that, there's going to be a second segment in which Louis is going to join me in a conversation, and we're going to talk about how those connections with psychology are informing AI research today and how it might help us understand the way that AI systems reason. And then at the end, we'll have some time for Q&A as well. So I'll get cracking with the initial part of the historical background then. And at a high level, I think I'd just like to observe to begin with that it's kind of obvious that we expect when developing AI systems that because they are trying to emulate human intelligence, there will be some degree to which they'll be similar to humans and might share some of the properties of human thinking. But at the same time, we do also allow for quite a bit of divergence from humans because of really obvious differences in their physical structure. Like if you compare the way a biological brain is set up compared to a silicon chipboard in a computer and the way that electricity runs through it, those are very different physical systems. And so you might expect that even if they become capable of doing the same things, that they will achieve it in very different ways. And it's a very open-ended question as to what the similarities will be in the end. But this conversation is going to explore some of the overlaps and differences. And so I want to just point out to begin with the extent to which AI has historically always been inspired by the way humans think or by other kinds of natural systems. So if you go back to the beginnings of neural networks, which were defined for the first time in the 1940s, which is pretty early on if you think about it, because even computation itself was only getting formalized in the 1930s by people like Turing and Church. So already in the 1940s, we're developing the earliest AI with neural networks. And I think by this point, because it's 70 odd years later, people might have lost track of how much that is actually grounded in the reality of human neurological structure. Neural networks might just sound like some sort of cyberpunk metaphor that people are using to try to make it seem like AI is human-like. But those original formulations were written by a computational neuroscientist and a neurophysiologist working together, and they were looking at the firing patterns of neurons in the brain and observing how those activation patterns could be modeled as on-off switches, like binary in computation. And so they developed a way of expressing that in a computational format, which became the basis for neural networks and the connectionist approach to AI. And that's gone through various cycles of boom and bust, as you might have heard from various like AI summers and AI winters, but it persists today as part of the core of the technology, which is underneath LLMs. So we'll be touching some more on that later on in the conversation. Sort of in parallel, but a very different approach, you then get symbolic AI. This is major in the sort of 50s and 60s, but again, it's something that's persisted in cycles up until the present day. The inspiration here was less to do with what's going on inside the brain and more to do with observing the behavior of humans when they reason. Because when humans try to do complex problem solving, we typically use language. We reason through problems in language, we explain ourselves and justify ourselves to each other in language. And there are various ways in which you can formalize linguistic expressions in a logical format. And so symbolic AI was particularly an attempt to express linguistic reasoning in like propositional logic or first order logic in various kinds of theorem proving systems, almost as if you were to treat language like it's a mathematical calculus. So the difference here is looking at the brain versus looking at behavior. Another analogy that people have used is with evolution, so outside of humans, but still in the natural world. One of the really interesting properties of natural selection and adaptation is the way that solutions to problems emerge without somebody having to consciously specify how to present a solution to a problem. So in natural selection or in an evolutionary approach to computation, if you're able to set up an environment in which you can randomly generate programs or organisms or randomly generate mutations to programs or organisms, so long as you've got some mechanism for distinguishing between the versions that do better and worse, then over time you can cull the things that are less optimal and end up with something that looks more like a solution to your problem. And another key analogy, which is again particularly relevant today, is reinforcement learning. So you might have heard of a paradigm of reinforcement learning through human feedback, which is an important post-training phase for LLMs today. And that is inspired by behavioral psychology. It's the classic idea of reward and punishment for training animals or training children or even adults in certain social situations. It's giving feedback signals in order to encourage people to behave in line with some sort of norm. So these are all grounded in knowledge of how humans and animals work. But in this conversation, we particularly want to focus on this thing, which is the System 1 and System 2 that was developed by Daniel Kahneman and colleagues from, I guess, the 1970s onwards through the decades. And looking at how that's been a framework to describe human psychology, and then looking at how it's being applied in particularly neurosymbolic approaches to AI. So let me quickly introduce Daniel Kahneman himself then. So Daniel Kahneman is a very famous experimental psychologist. A lot of his work was interdisciplinary. It can be hard to box him, but he won the Nobel Prize for Economics in 2002. And it's important to note as well that he collaborated with Amos Tversky, who would have shared that Nobel Prize if he hadn't unfortunately died quite young. But they worked together specifically critiquing so-called rational agent models. And the particular reason why, even though they were in experimental psychology, that Daniel Kahneman won the Nobel Prize for Economics, is that economics has a lot of so-called rational agent modeling, which I'll describe in a moment. And it's because they successfully critiqued those models that they were awarded that Nobel Prize. And a best-selling book, Thinking Fast and Slow, was published in 2011, which was a sort of retrospective on their research career. And so in that book, Kahneman observed that he was very struck early on in his career in the 1970s at the way economics papers talked about how they modeled people. And so a quote that he picked out was this description from an economics paper that the agent of economic theory is rational, selfish, and their tastes do not change. Now, this might strike you already as some sort of very weird idealization because humans are not perfectly rational, they're not always selfish, their tastes certainly change and so on. And part of the intuitions that we have today that this is an inappropriate description of people comes from the work that Kahneman and colleagues did to critique it, because one of the key ideas they're responsible for is this notion of cognitive bias. We're aware today of like bias in how we think of people who are different from us, bias in things like hiring practices, bias in AI models, certainly because of the data they're trained on, but also biases in things like how we reason through statistics, where human mathematical thinking tends to be quite sloppy because we didn't evolve for that kind of thinking. And this sort of idea of the ideal rational agent, I mean, it must go back at least to Adam Smith. writing about the wealth of nations in the 1700s. Maybe it's earlier than that. The reason why people are thinking like this is because in economics, people wanted to try to come up with a theory of how macroeconomics, stuff like the wealth of nations, GDP, arises out of individual microeconomic choices that particular people make day to day in terms of what they buy, what they sell, what they invest in, and so on. But if you're going to take an economics approach to that, you're going to be dealing with mathematics. And you can't realistically encode in mathematical formulae the full complexity of human behavior. So economists naturally come up with very simplified abstractions. And that's what this description of the rational selfish agent is. It's a simplified abstraction to try to make the maths tractable. And that might be useful, and those kinds of abstractions do work in scientific theorizing sometimes. But Kahneman was very particular to point out that there was a risk in taking these kinds of models too literally, that they would actually be the cause of potential harm. Because this view of human thinking is sometimes used as a basis for certain social theories or certain kinds of politics, which say that in the end, people, even in duress, don't need help or shouldn't be given help, because everybody is really making the choices that they want to make, and everybody should be ultimately individually responsible for it. And I think even, I'm not going to get into the social criticism or the politics of it, but most people would allow for a little more compassion than that. And Kahneman was very aware of that problem in his research work. But just looking at the psychological aspect of the theory, I want to give you a couple of examples that appear in their experimental work, which are also discussed in the book. So these are examples that would be presented to experimental participants. And the setup is there's a question or a scenario that you have to consider, and they're looking for people's responses intuitively to the setup. So here's one scenario to think about. Steve is very shy and withdrawn, invariably helpful, but with little interest in people or in the world of reality. A meek and tidy soul, he has a need for order and structure. And then you're to think about the question, is Steve more likely to be a librarian or a farmer? So because this is being presented as a question in an experimental psychology setup, you might already be thinking, this is a trick question, because we're familiar with that being the way that these things go in experimental psychology these days, unless perhaps you're an undergrad who hasn't come across this sort of stuff before. So you might already be thinking, what is the real answer that they're trying to get out of me? But in any case, it's very important for what we're going to discuss to think about what is the target intuitive answer and what perhaps is the more critically reflective answer that you should give if you were to second guess yourself. So have a think about the two answers you might give to the question. In this case, what you would find empirically is that people will tend to say that Steve is more likely to be a librarian. And then in the analysis of that, the psychologist, particularly if they subscribe to Kahneman's school of System 1 and System 2 thinking, would want to say, well, that's a problematic answer. Because if you take seriously the probabilistic aspect of the question, is Steve more likely to be a librarian or a farmer? You can't provide an answer to that question without a baseline awareness of how many librarians and how many farmers there are in society. Because if it would turn out that there are very, very few librarians and very, very many farmers, then statistically it would just be more likely that some random person like Steve is going to be a farmer rather than a librarian, regardless of his personality, because he would just have few opportunities to become a librarian. Now, in thinking of that response to the intuitive question, you might think, is that a fair analysis that the psychologist would give? And there are lots of caveats and criticisms that have been given in the literature. And I think those are some of the most interesting questions that are being raised by this research. And maybe we can discuss those in the Q&A. So if you have those thoughts, I would encourage you to put them in the chat. But at the moment, I'm just going to present Kahneman's framework without necessarily endorsing it. Another example, which might be slightly less controversial, comes from arithmetic. So here you're asked to consider that a bat and a ball cost $1.10 in total. The bat costs $1 more than the ball. And the question is, how much does the ball cost? So again, you might just take a moment. You may have seen this before. This has been shared a lot online, but whether you have or you haven't, you might just take a moment to think, what's the intuitive answer that's being targeted here? And what's the correct critically reflective answer? So the intuitive answer people will typically give is that the bat costs $1 and the ball costs 10 cents. But if you think about that, that doesn't satisfy the question. Because if the bat costs $1 and the ball costs 10 cents, then the bat costs only 90 cents more than the ball. But the bat has to cost $1 more than the ball. So the right answer must be that the ball costs 5 cents and the bat costs $1 and 5 cents, because then the bat is $1 more than the ball, and together they cost $1.10 in total. So this is perhaps less controversial than the first example because there are fewer complex social variables. It's a maths puzzle which has a clear right answer. I've seen some interesting criticisms of it which actually describe it a little bit in the vein of a like in a magic trick where someone forces a choice with a psychological trick, or somebody who's doing a card trick and they make somebody pick a card. There are some aspects of how the language is presented in the experimental setup which might be critiqued that way. But again, those are side issues which we might bring up later. But I'm just trying to get you feeling the sense of how they're thinking about intuitive responses to questions and critically reflective responses to questions. So that is the basis of what Kahneman calls System 1 and System 2. Now, Kahneman is very careful in Thinking Fast and Slow to say that System 1 and System 2 are not sort of formally or rigorously well defined. They're not particular places in the brain that can be localized. They're not specific networks that can be isolated from each other. He actually describes them as characters, as if they were characters in a novel. They are explanatory abstractions that he's just developing in order to help us be reflective about the way we think about problems in different ways. And for that reason, I think the best way of really getting familiar with the difference between System 1 and System 2 is to just go through some comparative examples. So System 1 would do something like assess the relative distance of objects. You just look around the room, you know instantaneously the window is further than the door. System 2 would direct attention to objects of interest. So maybe there's a blemish on the door, you're interested in the detail of it, you direct your focus at it and look for more specifics. System 1 would complete a cliche, bread and fill in the blank. Maybe some of you will think cheese, maybe some of you will think circuses. System 2 will try to find the right words for an idea. So there's something you want to express, you've got a thought which is on the tip of your tongue, but you have to root through your vocabulary to find the right way of phrasing it. System 1 would respond reflexively to sensory input. You taste something, you instantly know what it is, or you hear something, you instantly know where the sound is coming from. System 2 would be trying to identify unknown sensory input. So you taste something, maybe with a blindfold on, you know what the flavor is, but you can't say it. So you have to try to make connections and think about it. Or you hear a song and you've forgotten who it was who wrote it, and you root through your memory to try to find who it was. System 1 does basic arithmetic. It's just rote recall from memory, like 2 plus 2. System 2 does complex arithmetic. You don't know by heart what 17 times 52 is, but you could work it out if you were given pen and paper or even a calculator as a tool. System 1 would be just reading text aloud. System 2 would be counting the number of words in a text, like looking at a piece of paper and finding out how many times the occurs. System 1 would be driving a car on an empty road. System 2 would be parking a car in a difficult spot. System 1 would be playing a piano as a virtuoso. System 2 would be playing a piano as a beginner. And one of the things I actually want to highlight with these final few examples is that there is this broad dichotomy between System 1 and System 2. But they're not always entirely separate or always entirely responsible for different things. One of the characteristic relationships between System 1 and System 2 is that System 2 deals with novel problems, but if they're things that you can become skillful at through practice, over time, System 2 will offload an ability to System 1 as it becomes more intuitive. So when you're playing a piano as a beginner, you're working out all of the muscle coordination. That's something you need a lot of conscious awareness of. But as it becomes second nature, that feeling of second nature intuitive skill is System 1. So if we were to then try to summarize this distinction in some key properties that are shared by all of those examples, and again, this is not a formal definition, but this is just trying to find some consistent features. System one is fast. You give it a problem to solve. The experience of its solution is instantaneous. When you're doing any kind of perception, you feel like you are instantly aware of the things you are attending to. System one is also generally subconscious in that it happens without you having to think reflectively about it. It's just system one is what makes your conscious awareness present in the way it is. System one is also automatic, it's reflexive, and it deals usually with familiar problems. This is related to the point I was just talking about with system one being responsible for skills. Over time, as things become more familiar to you, system one takes on more responsibility because familiarity is what breeds the system one competence. And that's also related to system one being a sort of heuristic problem-solving system. The heuristics are involved particularly because if you're dealing with things that are familiar to each other, then with each example that you get, a heuristic system is looking for the familiarities in each example you come across. And then when you come across a new example of that problem, you predictively think, okay, this is going to be similar to stuff I've come across before. It's that kind of predictive heuristic which system one is applying. System two, in contrast, is generally regarded as slow. Exactly what the speed of system two is actually varies quite a lot in comparison to system one because it depends upon the complexity of the problems it's solving. System two is conscious. You tend to apply system two reflexively because you know there's a problem that you need to solve which system one isn't dealing with. System two is deliberate rather than automatic. It tends to involve cognitive effort. It tends to be less adept at multitasking. So you're very aware of the fact that you're in system two thinking mode. System two deals with open-ended problems rather than familiar problems, particularly in the sense of problems that are novel, things you haven't come across before, things you can't compare by analogy to previous experience. And system two is also logical. And I think one of the important things to distinguish here with the heuristics is that system two is open to edge cases. It's open to the unfamiliar. And we tend to use logic a lot to try to examine how things are fundamentally different or unique from other stuff we've encountered before. So at this point in the conversation, then, I want to bring Louis on for a chat, and we're going to spend the next 20 minutes or so talking about how system one and system two are being used in neurosymbolic AI. So I started thinking about this conversation because as an AI researcher, I've noticed in the research literature lately that lots of people are referring to Kahneman as inspiration. And system one and system two are a hybrid of two systems in human cognition. And neurosymbolic AI is an approach which says that the best AI systems will be a hybrid of neural and symbolic tech. So there is at least the open potential for an analogy there, and we're going to discuss the extent to which it's useful. But to begin with, Louis, could you talk people through how to understand what neural and symbolic models are if we just understand them separately to begin with?
Yeah, that's right. So, okay, you've alluded to some of this already at the early parts of your presentation, but there's a difference of opinion in the history of AI research. Two schools of thought which have had varyingly heated debates throughout history, especially in the 80s, as to how you should build AI systems. And one of them is neural computation, the other is symbolic computation. Neural computation is obviously, by the name, inspired by the brain. And it essentially works by having lots of very simple units that are analogous to neurons. So they're more idealized than anything like a neuron in the human brain. And these units send information to each other in the complex configuration of the way they're networked together. And as that information gets passed around, something that came in as an input on one end gets returned as an output on the other end. And they are a completely different paradigm to symbolic computation, which includes most of software that is not thought of as AI as well. So One of the features of neural computation is that it requires learning, and that's because it's essentially impossible for a human to program a neural network. In theory, you could try to specify which neurons should send which amount of information to all the other neurons in the network, but it's not something that any human can really do beyond tiny networks that wouldn't be able to produce anything meaningful. So you're forced to use learning, and that's why neural networks sit inside the machine learning paradigm to AI and to software in general. Another important feature of neural computation that distinguishes it from other sorts of computation is that it has a fixed runtime. So no matter what the input is, no matter how kind of difficult the thing you're trying to solve is, exactly the same sequence of bits of information are passed throughout the network, and it all takes exactly the same amount of time. However you measure computation, the same number of operations. It tends to be very good with noisy and incomplete inputs. And this is something that in the history of the debates between neural and symbolic computation was one of the real ace cards of the neural side, that they could deal with inputs that had bits that were kind of mistakes in them, like natural language text with typos or words missing, or maybe if you're trying to understand images and the image has been degraded slightly, they were much better than the symbolic side at handling that kind of thing. And another feature, which is one of the weak sides of neural computation, is that it's very hard to understand what they're doing and why they're producing a given output. If you look inside them, you see all these pattern of one neuron sending some amount of information to another neuron, and there's, I mean, in large networks today, there's hundreds of billions of these neurons. So it's not quite impossible. There are some lines of research that try to understand this, but it's a very difficult problem to try to say what that all means, or try to summarize that exchange of information in some way that makes sense to humans. And the examples that are most kind of prominent today of neural networks are also the ones that are most prominent of AI, all the recent AI applications. LLMs. So LLMs, we say, it's kind of a subtle point, but when LLMs choose, the specific thing of LLMs choosing the next word to use, that's a single pass through a network, neural network. LLMs more generally is a bit more complicated, but just the specific thing of choosing the next word, that's a neural computation. And more recently than that, also image and video generation. These are kinds of things that would be completely impossible with the symbolic side, but have turned out to be quite doable on the neural side. And in contrast to all this, symbolic computation, all right. In contrast to all this, symbolic computation includes all of software, as I said, all of software that isn't AI. So everything that a human programs. And that means you have to have an algorithm, the human has to have some idea of what the thing is going to do and how it's going to do it. And that's what the human uses to program it. The runtime, in contrast to the neural computation, the runtime can depend on the input. And this, in some way, makes more intuitive sense from an AI perspective, though maybe this is something we can get into in the system 1, system 2 thing. But if you ask, say you're asking a large language model a yes/no question, so that only has to return one token as an output. No matter how difficult the question is Paris the capital of France, versus if the question is some really difficult question, it will take exactly the same amount of energy, the same amount of computation, the same amount of time to answer that. Whereas if you have some symbolic system, very often the runtime can depend on the input and will tend to be more difficult for more difficult inputs. Then as just a flip side of those two neural properties, it's very bad with noisy and incomplete input. It tends to maybe give the wrong answer, or maybe just give an error and not be able to return an answer, like some of the early attempts at understanding language with symbolic systems tended to do that. If there was a single typo or there was a word was misspelled, the whole thing would just break. But the plus side is that because you designed it and you know exactly what algorithm it's realizing, you can explain very well what it's doing and why it did it. And examples of them, I mean, you could almost pick anything, but Excel spreadsheets, they are coded by humans. They follow an algorithm that humans know. And the network stack, meaning like all of the various bits of software that handle the internet, are all designed in this symbolic computation framework.
Great. And so I guess through the history of AI, there's been a lot of competition between neural and symbolic approaches. But one of the interesting research programs at the moment, and one which we're particularly involved in, is neurosymbolic. There are lots of different ways of potentially hybridizing these approaches, and a little bit like with System 1 and System 2, it's not the easiest thing to define these things formally. But could you perhaps give us a sense of how some people are trying to combine neural and symbolic together?
Yeah. So I mean, that's an obvious thing you think of when you look at these two, and the strengths and weaknesses seem to complement each other. Yeah. So I mean, one example that comes to mind, and it's interesting because it's fits into the history of this, and it also is maybe, as we might get to, one of the better examples that analogizes to System 1, System 2 is AlphaGo. So this was a program from DeepMind about 10 years ago that played the game of Go. A variant also played the game of chess. So you can almost essentially think of the same sort of problem, playing chess and playing Go. And it used a combination of neural components and symbolic components. And roughly speaking, the neural components handled the aspect of having a guess as to what a good move would be. Being able to look at a board and just predict a move without explicitly calculating what the future positions are going to be. And then there was another component, was the symbolic component, that did explicitly calculate what future positions would be. And they are obviously two things that human players do when they're playing something like chess or Go as well. I mean, a chess grandmaster, for example, can look at a board and would play, if it just played the first move that came into their head, they would still beat me, even me calculating many moves ahead as I could. But then also chess grandmasters, when they're playing at their best, do calculate moves ahead as well. So they're using a combination of these two methods. And that was what made AlphaGo so successful, and it was such a landmark in AI, in the progress of AI. And I think if we talk about it analogizing to System 1, System 2, I think this is one of the best examples I can think of. It's also interesting to see how they phrased what they had done, how DeepMind talked about AlphaGo at the time. And the story was all about the neural side, all about the deep learning bit. And that's because that was the bit that was new at the time. I mean, the symbolic techniques they used were things people had been using for at least a decade before, and they had kind of worked by themselves. But the missing bit was this, like, can you just model something about an intuition as to what the next move should be? And neural networks, particularly at the time, convolutional neural networks came along and were just slotted perfectly into that missing piece in AlphaGo. So DeepMind phrased it as, this is a big success for neural computation. Really, it was a success of a neurosymbolic system, a system that combined both of them.
Right. Am I right in thinking as well that, like, in terms of this property of symbolic computation of the runtime, maybe depending on the input, that like the symbolic tech they used in AlphaGo had been around for ages, but it couldn't solve the problem on its own because of a complexity issue, because of the nature of the game. If you try to search all of the possible moves you could make, the size of the energy input you would need to solve the problem was just too extreme, right? And so
Yes,
the
right.
neural element was a way of still being able to take advantage of some of that search, but being able to use sort of intuitive shortcuts towards the more useful moves, right?
Yeah, that's right. Yeah. And if you look at like the earlier versions of it that played something like chess, it's kind of funny almost to watch how they worked. Like they could calculate moves much faster than a human, but they considered all these completely pointless moves that a human would never consider, and so they wasted loads of computation going off in meaningless directions. And the thing that humans use to guide the search that they do, the very limited type of search that we do, is we only look in directions that seem promising. And that's the bit, yeah, that the neural system added.
Right. So yeah, I think there's a really interesting opportunity for these clever trade-offs. But let's dig a bit deeper on exactly how this analogy might hold up with System 1 and System 2 in particular. So returning to the list we had before, people in the recent research literature specifically want to make the connection between system 1 and neural models and system 2 and symbolic models. And actually, even more specifically than that, most people are describing LLMs as system 1. But let's just quickly go through these properties and think how much they actually overlap with AI today. Do you think it's fair to say that neural models are fast, or at least faster than symbolic models?
That is, it's kind of a subtle question. I mean, on the face of it, the answer seems obviously no, because sometimes very big neural networks can take a long time to run. Sometimes you can write a short Python program that will be like microseconds to run. The point, if you're trying to be sympathetic to the analogy, you could say that the fixed computation size is something like being fast, that you don't have to worry about it taking a very long time. You know exactly how long it's going to take. And if you look at, on symbolic systems, not always, but often it might be the case that if you look at the very worst time it could take for the hardest possible question, then that's actually quite slow. But in practice, it tends to be a bit faster, but you still have to worry about this like worst case complexity or worst case runtime. Whereas the neural system, you don't have to do that. So maybe somewhat of a loose fit.
Yeah, although the fast and slow was already a bit loose with system 1 and system 2 included, so it is perhaps fair. Do you think it's at all useful to describe neural models as subconscious processing, or is that an analogy too far?
I think basically no. I mean, conscious is such a loaded word, and people think that LLMs might be conscious and all sorts of things like that, which we obviously don't think.
Do you think there's any connection to the explainability of the models?
Yeah, that is maybe an angle you could take about it. That there's something about system 2 is conscious because it came from humans who consciously programmed it. So like the algorithm existed in a human mind consciously before it was put down, it was encoded into the computer. Whereas for the neural system, no one even really knows what the algorithm is, if it is an algorithm really at all. And it just sort of arose out of the training. So it's kind of, maybe you could call it unknown versus known or something like that.
Yeah, that's fair.
Yeah.
And how about automatic versus deliberate would have been the comparison with system 2? I'll just bring the other side up because it's easier to see them together.
Yeah, I don't really see much of a connection with that either.
I guess it's hard because if not just in terms of consciousness, but if you don't have some notion of executive control and choice making and decisions, it's very difficult to see how that distinction, like all computers seem to run automatically once you set them running, right? So that's a particularly tough one.
Yeah, it implies something like that's allocating resource to different things it's executing, and it like doesn't need to allocate very much resource to the neural one or something. But I don't think that really fits that one.
And how about dealing with familiar problems versus open-ended ones or novel ones?
Maybe somewhat of a fit again, because of the learning element, that the fact that you need to learn the configuration for a neural network means that there's something familiar about the problem you've seen. It has to have seen something similar before, and that's what it uses to solve the problem. Symbolic being open-ended, yeah, that's a bit more tenuous, but potentially, I mean, the idea being that you can write a piece of code that works on a certain problem, and it actually works on a much larger set of problems that you didn't really consider, but it still works well in them. Maybe you could say that. So again, sort of half marks, 50% fit.
Yeah. And then how about the heuristic versus logical comparison?
Yeah, this to me seems, and I'm sure you have a take on this as well, seems to me to be the best fitting of the properties. That there's something kind of on a high level, like vague, fuzzy, approximate about the neural method. And that is both the strength that lets it work with noisy inputs, and also the weakness that means it is a bit imprecise sometimes. Versus the logical one, which means you have to have a perfect input or something that conforms to a rigid structure as an input, but it's guaranteed to be exactly right when you do have it like that. I wouldn't want to say it's an exact fit. I mean, because both neural and symbolic can be quite, the diversity of what they can be is quite large. But in terms of the systems that normally come to mind with neural and symbolic, I think this is a reasonable fit.
Yeah, I think as well, I didn't mention it in my earlier slides, but particularly as I've been listening to some interviews with Daniel Kahneman lately, he tended to talk a lot about the role of surprise in human cognition. And I think perhaps, heuristics are not great for dealing with surprising things because it's all about analogizing to previous experience. And so there's an important respect perhaps with which logical reasoning can be applied to surprising stuff. But that's exactly how that gets worked out, can be complex. But yeah, I mean, one of the interesting things about Kahneman actually is that I don't know if he commented on it in print towards the end of his career, but certainly in interviews, he said that he thought perhaps the system 1, system 2 analogy had been taken up in a confused or imprecise way by AI research. He felt particularly that it was a problem to describe system 1 as non-symbolic in the way that neural systems are, because at least in humans, there's some degree of language understanding, which is in system 1. Exactly what it means to say that language understanding is symbolic is a very thorny question, because language is a multifaceted ability. Which aspects of it are symbolic in the sense of symbolic computation or symbolic in the sense of just words being symbols? It all gets a bit of a mess with the terminology, but that was one of his criticisms. But I think then, so there's some, like you said, it's maybe 50-50. There are some imprecisions here. I think from my appreciation of the research, people are generally trying to leverage the analogy just because you get credibility for the association with a human cognitive framework, but people tend not to develop it too far. But at least in our research, we're definitely on board with the idea that some sort of dual system hybrid is really powerful for solving certain types of problems. So if you were going to try to salvage like one property for system 1 neural and another property for system 2 symbolic, what is it that you're looking to combine together in the sort of systems you're designing to solve the problems you're solving right now?
Yeah, I think it's this point about messiness, fuzziness versus precision, and if it's by itself, brittleness. And if you look at the types of applications that we're designing solutions for, like something that involves understanding a long, complicated technical document about regulation, for example, you're dealing with both of these problems. You're dealing with there's some core structure to the meaning, which is logical and which is precise, but the whole thing is expressed in natural language, which can be, worded in lots of different ways, and you have to deal with the fuzziness of that world as well. So I think the cleanest takeaway from the whole analogy is that it makes sense to use different systems, and in the computational side, that means neural and symbolic systems for these two parts, to handle the different aspects of problems that have both of those elements to them. Some problems are solved adequately by entirely neural or entirely symbolic systems, but problems like the one of regulation through natural language, it makes sense to use both.
Yeah, and I think as well, something we discussed before is like there are multiple dimensions to making the choice for what sort of system to use. And so we've particularly been thinking about sort of capability, which would be, you might measure it in terms of accuracy, right? But you might even find yourself in a situation where you could use a neural system or a symbolic system, and they might solve the same problem just in different ways. But perhaps they have properties which would mean, like for product reasons, you would want to choose one or the other or combine them. And so I think like in the sorts of like regulated industry domains, like if we're trying to use our tech to understand insurance policies, for example, that using symbolic models is really important for explainability and auditability, because like you said earlier, if some of that stuff is programmed or it's transparent and you can read it, then you understand how the system works, and that can be very important for telling downstream users how a decision was made or something like that.
Yes, exactly, yeah.
Okay, so we're at question time. So I'm just gonna stop sharing the slides and then we'll dig into the chat to see if anybody's asked any questions. Yeah, so let's take this first question then. There should be a system or layer that enables the human brain to switch between the two systems, even for the same context or situation or use case. Any thoughts on this? This is definitely something which, I mean, it came to my attention lately because while I was doing some research for this webinar, I was looking at a neurosymbolic system designed by a research group at IBM. And they talked about having system 1 and system 2, but they also talked about something which they described as metacognition. And the metacognition component was specifically responsible for deciding when system 1 and system 2 should apply. And in their particular setup, which was not necessarily informed by Kahneman, although they made the reference, in their setup, they always first applied system 1 to a problem, and then they would use some heuristics to guess whether the system 1 solution would be a good one. And if the heuristic said, yeah, it's probably a good answer, they would just stick with system 1. But if the heuristic said, maybe that's a bit dodgy because of the element of surprise or the element of novelty, then metacognition would say switch to the system 2 solution, and then they would use a symbolic method to solve the problem. In Kahneman's work on psychology, I'm not sure exactly about, I don't think he would have separated out like metacognition as a third factor. I would imagine that that is probably a responsibility of system 1. I don't know if you've got any further thoughts on that, Louis.
Yeah, I believe this is something that I've heard criticized actually about the system 1, system 2 framework, that it's not articulated very clearly how they cooperate and when it's decided to use one or the other. But you know, that example you give in that SoFi IBM system, that sounds like a reasonable way to do it actually. And he does give examples like this, doesn't he? That system 1 tries something, it doesn't seem to work, and then system 2 kicks in. And that also relates to the notion of surprise that you tried before. Like when you're just chugging along about your business as normal, it's all system 1. And so when something unusual or maybe startling or frightening happens, that you might move over to system 2.
Yeah, I guess the interesting thing there is sort of where does maybe some kind of feedback come from? Because often in the experimental setups that Kahneman was using, people will give an intuitive answer and then just be completely satisfied with it and not think there's a problem, right? And then it's then when something from the outside comes along and someone says, actually, do you want to look at that answer you just gave? And this doesn't work. And that's a piece of negative feedback, which then stimulates somebody to apply system 2. So maybe there's an open question about how to get that feedback into the system to do the switching. But yeah, this second question is perhaps one for you as well. So referring to runtime, depending on the input, how is this different from event-driven architecture that AI native teams and companies are already working on, but using LLMs?
Event-driven architecture. Could I don't know if the person can elaborate on what that.
Yeah, perhaps Aditya, if you're still there, you might elaborate on specifically what you're referring to by event-driven architectures, and we can pick up that question. Let's see what else we have. Okay, here's a meaty one perhaps. So from Matt, if system 1 and system 2 are endpoints on a continuum rather than discrete modes, doesn't a fully neural architecture have an inherent representational advantage since it can occupy any point on that continuum fluidly, whereas a neurosymbolic system with a hard handoff between neural and symbolic components is forced to discretize what is fundamentally a graded phenomenon?
So I wonder if this has in mind the neural system being some type of LLM with ability to call other tools, which could be neural or symbolic. And actually, this gets to a point that we touched on, but we didn't actually go into, which is that LLMs are kind of, they don't fit totally in the neural side, because they, just in the question of deciding the next token, they're just a pass through a neural network, but then you can iteratively keep making new tokens. So they're basically a neural network inside a while loop. And although that's a very small symbolic element, it changes the picture somewhat. And it means, for example, that this fixed computation size doesn't apply if you consider the LLM answer being like as long as it likes, which is normally the case. If that is the model we're thinking of, that it's an LLM that decides which other things to call, I mean, that is essentially like using the LLM as the orchestrator between lots of other components, some of which could be neural and some of which could be symbolic. Depending on which neural and symbolic tools or systems you use there that the LLM can call, I may call that a neurosymbolic system. I think it may count as a neurosymbolic system. But then you do also raise, I mean, it sounds like ultimately it would be like a more neural system than a more symbolic system, and you would have issues perhaps like if you needed to account for, you to explain why you used a given tool and that decision was made by an LLM, you might return to the issue of like, what's the audit trail or the explanation there. Yeah, so I kind of read a bit into that question, but I hope that that was
no, I think just to pick up on that last point you made as well, something that we also talked about previously, but which is something I'm still developing my thinking on, is that although I probably agree that there are aspects of System 1 and System 2 that are on a continuum, something which I think is really important that's not accounted for in Kahneman's framework is the difference between personal and interpersonal cognition. And a lot of what we're doing, particularly with language, and particularly when giving explanations and justifications for things, is participating in a social dynamic. And that's something, you know, to what extent is there computation that happens interpersonally? Maybe that's an awful philosophical question, but it's one which is perhaps worth asking. And then to that extent, you know, it's difficult, I think, to reduce everything to maybe at least a single neural architecture individually. I don't know if you might still be able to represent that interpersonal dynamic as neural fundamentally. But yeah, that's something, at least I think it's a question which is just not addressed in the framework.
Yeah.
Cool. Well, it looks like that's all of the questions we had, and we are slightly over time in any case. So I hope everybody enjoyed the conversation. I thought those were really good questions. Although, oh no, I missed some questions actually because they didn't populate the tab again. I had to click away. Is there anything important we missed? Is there anything? So I guess unless we are encouraged by our overseers, I probably don't want to push too far into extra time, unless there's anything you particularly want to pick up on in the chat, Louis. I think it's probably fair to leave it there since we're over time anyway.
Yeah, that sounds good.
Okay, well, thanks everyone for joining. As I said, I hope you enjoyed it. I thought it was a good conversation. Thanks for your questions and your time and your interest. And I believe there are some links available to the lab website. So do follow up with us if you're interested. Thanks.
Cool. Thank you, everyone.